We now want to look at position, velocity, and acceleration with sinusoidal motion. So let's go back to the spring example, and we have our spring stretched and we let it go and it's going to move upward. If we start our stopwatch immediately upon release, then this position versus time is going to be a negative cosine. So x of t is going to equal negative cosine omega t. And I'm just arbitrarily at this point going to let the amplitude for the position be negative 1. Okay. Now the units on the y-axis here are arbitrary, and I'm also going to let omega be 1 for our example as well, but I'll keep omega in the description mathematically so you can see how the derivatives are working with it. So if my black line, okay, or I should say my black curve rather, my black curve here represents my position versus time. The red is going to eventually represent the velocity versus time, and the blue is going to represent the acceleration versus time. And we want to see how these are all related to each other. So if I start with my position versus time, I know that if I take the derivative, then I'm going to end up with the velocity. So if I take the derivative of my position versus time, the derivative of cosine is negative sine. The derivative of negative cosine is sine. So this is going to give me a sine function, and then I have to take the derivative inside via the chain rule, so I'm going to get an omega out front. So my red curve represents omega sine omega t. Okay? In other words, whatever the amplitude of my position versus time is, it's going to get multiplied by the angular frequency omega. If we let omega be 1, then it stays 1 and the units on the axis here stay the same, but you see how it works. Right? If my position is a negative cosine, then my velocity is going to be a sine function. And these are going to be out of phase by 90 degrees, right? These are going to be out of phase by 90 degrees. Oop. Let me write it like this. Okay, and you can see that as where my velocity is at a maximum, my position is at 0, and where my position is at a maximum, my velocity is at 0. And so sine and cosine trail each other by 90 degrees. And that's exactly what we see both mathematically here and graphically here. Now what about the acceleration? Right? So again, that's the velocity. My acceleration is going to be the second derivative. So if I take the second derivative of this, then applying the chain rule again, I'm going to get an extra omega out front, and the derivative of sine is cosine. Make that a little bit better. So we have omega squared times cosine omega t. And again, this is a cosine function, this is a sine function, so these two are also going to be out of phase by 90 degrees, all right? But if this is out of phase with this by 90 degrees, and this is out of phase with this by 90 degrees, then that either means that this and this are in phase, or they're out of phase by 180 degrees. And as you can see from the graph, where cosine has a maximum or minimum, negative cosine, or its opposite, is going to have a maximum or minimum on the opposite side of the equilibrium position. So if my position starts down here with the negative cosine, my acceleration is going to start with a maximum with the cosine function. So these are actually out of phase by 180 degrees. So with each derivative you take, you're going to become more out of phase by 90 degrees. Okay? So where your position function is, your velocity function is going to trail that by 90 degrees, and your acceleration is going to trail it by 180 degrees. Okay? And again, it just simply comes out from the derivatives here And this is what the plot of the position, velocity, and acceleration look like. Out of phase by 90 degrees with each other, and the position and acceleration are out of phase by 90 degrees or 180 degrees with each other. Now I should mention something here, okay? Where is my acceleration maximized? Okay, at what points do I experience a maximum acceleration? It's at the end points here, where my position is at a maximum and minimum. Then my acceleration is also at a maximum or minimum in true value form. But if I just want the magnitude of my acceleration, okay, if I just want the magnitude of my acceleration, my maximum accelerations are going to occur here, 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 and then again down here. And these are when my positions are maximized, right? If I just take the magnitude of my position, I get maximum magnitudes here, here, and here. And so whenever my position is maximized and my acceleration is maximized, then both of those are maximized. But also look at the velocity. When this is maximized and this is maximized, my velocity is 0. So we call these points the end points or the turning points, and these represent the points where it's the lowest or the highest. And because my object has to turn around, right, it's moving this way and then it turns around and moves it back up this way, eventually the velocity had to go to 0, but it's at that point where the acceleration the object experiences is actually maximized because the object has to reverse its direction. So it has to experience a very large change in velocity at that point. Even though the magnitude of the velocity is 0, the change in the velocity is very large, and thus it experiences its maximum acceleration at the endpoints. Hope that helps, and we'll see you next time.